Okay, we're talking today about LeChatelier's principle, which is all dealing with equilibrium. And we know that equilibrium is dealing with how in a closed system, either a reaction is occurring the same in the forward at the same rate as the backward reverse rate, or if we're just looking at states of solids like you saw in your web lab yesterday, we've got the states going back and forth seamlessly. So equilibrium, remember, is when the reactants form the products at the same rate that the products form the reactants. Again, we're not dealing with concentrations here, we're dealing with rates. So the forward and the reverse rate are the same. The two most common occurrences is when we have gases in a reaction, or when we have chemicals that dissociate in water. Which, if you remember, dissociated in water means that we have an aqueous solution, and we symbolize that with an AQ. Equilibrium is quite a bit like a teeter-totter. So if you remember back to elementary school, we can have two students, put them on the teeter-totter, and if they're relatively the same size, they can go up and down as they please, and if they're about the same size, they could really both be sitting on it normally without moving their legs, and it wouldn't be going up or down. But we get somebody that comes in and puts the teeter-totter out of balance. So here we have one student coming in, and they've put it out of balance. So Sarah B is way up in the air now, and Sarah W is on the ground, and they don't want to be that way. So in the teeter-totter, what we have to do is return back to equilibrium, just like we do in chemical reactions. Something has to happen, like you saw in your web lab yesterday, for it to get back the way that it was. So if we have Henry's a big guy and we've got two smaller girls, Sarah and Sarah, we can put the two girls on one side and Henry can go on the other, and they're all happily playing with one another now. So this all brings us back to chemistry and LeChatelier's principle, and that's when a system is at equilibrium and it is disturbed, the system will correct itself to restore equilibrium. So we've got this equal forward and backward rate, but oh no, something happened. We've added something to it. Maybe we've changed the temperature. Maybe we've added more of one of the compounds. But something's happened so that it's no longer in equilibrium. Well, when that happens, the system is going to go do something so that it gets back to how it was before. So the backward or the reverse and the forward rates are the same yet again. And this isn't a conscious effort. We don't think that atoms can think and process and have emotions or anything like that. We've talked about that before. We often talk about them in terms like they do. We give them human qualities. That's what we do with things. We give things human qualities. But really, this is just happening so nature can become more stable. So, what are we talking about here? We're saying that an equilibrium reaction is just like our teeter-totter. When the kids were given a new set of conditions, when Henry came in, they figured out a way to make it work again. So when a reaction is given a new set of conditions, it will make it work out too. Again, this isn't a conscious thing. It's not thinking about how it's going to do it. It's just that the system, the universe, starts going towards more stable. So what does this mean? The teeter-totter was initially at equilibrium. That was our Sarah and Sarah. The equilibrium was disturbed when Henry came in, and the system fixed itself with a new equilibrium, though it was different from the original equilibrium because we have now all three of them. So the initial rates are not necessarily going to be the same as the final rates, except that we're going to have equal rates between one side and the other. So let's look at some chemistry. If we have an iron 3 ion and a thiocyanate ion forming iron thiocyanate, and we have the iron 3 ion increased. So I increase the concentration of this part. Well, that's going to put me out of equilibrium. So the forward reaction going towards the FeSCN2 plus has to increase to set off the change. So if I have more of the iron 3 that's putting me off balance, see if I can add my colors in here. So I've put it off balance because I've added more. So what has to happen is more iron thiocyanate has to form for this side to go back down and that side to start going up. So the iron's going to bond with more of the SCN ion to form more of the iron SCN ion. If I decrease the concentration of something, so what if something was added that bonded with the Fe3+, which would then decrease the concentration? So if we're looking at that same reaction as above, or in the last slide, I have now decreased my Fe3+, so I went from a nice level line to one that's lighter on this side because there's less of it. So what's going to have to happen is more of my FeSCN2+ is going to have to decompose so that I have more Fe3+. So I'm going to have my reverse reaction increasing. The rate of the reverse reaction has to increase so that I get more Fe3+, so that that side will go down, this side will go up, and I'll be level again. Oops. Okay. Okay. If we have a gaseous equilibrium, we can increase the pressure, which initially shifts to the side with the least number of moles of gas. The reverse has to happen to get it back to equilibrium. So I have to look at my number of moles, so balanced reaction would come in handy here. My least number of moles, so then to get back, I need to have the reverse happen. If I decrease the pressure, we're going to have an initial shift to the side with the most number of moles, and then the reverse must happen to get that back to equilibrium. So I'm looking not only what's happening here right away at the beginning, but what has to happen to get it back at the end. If you add a catalyst, we know that that changes the activation energy, it decreases it, but that will not affect the equilibrium. Again, it reduces the activation energy in both directions, so it's not going to have an effect on the equilibrium. The rates will, though, both speed up, so both the forward and the reverse are going to be sped up. The temperature can be tricky because we need to think of our enthalpies from 2 units ago. If the temperature of a system is increased, both the forward and reverse reactions increase, but at differing rates. The reaction shifts to the more endothermic part of the reaction because it has the higher activation energy to overcome. If the temperature of the system is decreased, the reaction shifts to the more exothermic part of the reaction. Remember, exothermic, we deal with an enthalpy change being negative. Endothermic, remember, is positive because we have a lower activation energy to overcome. And that is all.